Hi everyone, in this video I'll be covering section 3.2, which is on the product rule and the quotient rule. Many people I think noticed when they went through and did the 3.1 homework that you can't just apply those techniques to any type of function or any type of equation. For example, some people, if they saw, two functions multiply, they just went ahead, took the derivative first, derivative the second, multiplied together, and then wondered, oh, wait a second, why isn't my answer right? The answer to that question is the techniques that we learned in section 3.1 didn't apply for when we had functions multiplied or divided. We only, learned the power rule, which applies to a function, so a function, I should say, a variable, raised to a constant. We learned the exponential rule, which is really a constant raised to a variable. We learned that if we have two functions added or subtracted, that's okay to take the derivative of the one, the derivative of the other, and then add or subtract. And we also proved why that's true. And we also learned how to take derivative of a constant and proved why, if you're taking the derivative and you have a constant multiplied, not a function multiplied, a constant multiplied, you can pull that out. So key thing to notice is that in each one of these sections, you learn different techniques for different types of functions. What ends up happening, or what the challenge ends up being, is determining, okay, well, what can I use and where? And another challenge is eventually you'll have multiple techniques that you can use on something. So in 3.1, we saw we had things that were multiplied, but then if we distributed, we could just use, maybe the power rule or the exponential rule on it. In section 3.2, we'll learn, oh, if two things are multiplied, then we can actually just follow the product rule and find the derivative. So you're going to find there are multiple techniques. The key thing is going to be noticing, okay, well, what do I do and when? So think about this as we're adding more tools to our toolbox on differentiation. We have a lot more to add. You're going to want to understand the reasoning and notice kind of small things in order to be able to carry throughout them. And throughout all of this, you will, need to apply some prerequisite skills at all. And if you forget anything, ask questions. So on discussion boards and in office hours, I'll say, oh, just so you know, this is prereq, etc. I don't mean that I don't want you to ask that. I just tell you that so then you know if it's not covered very specifically in the notes, that's why. But it's not a bad thing to ask. Everybody forgets things. Some of you haven't taken math maybe in a while. Some of you maybe don't remember it, or maybe you didn't cover it at the time. So it's totally fine to ask. Okay, anyway, let's get to the 3.2 notes. In this video, I think I'm just going to go over the product rule, and then I'll make a separate one for the quotient rule, just kind of split it up a little bit. All right, so first, product rule is what we use when we have two functions multiplied by another. So if you're looking at work and you say, I see two functions multiplied, that should clue you in, I can use the product rule on this. Let's explore that a little bit. All right, so looking at this table that I have here, I should probably make this so I can write. You can see I have one function, so an f of x function and a g of x function. In this first part, I have the f of x function. When I take the derivative of this, I get 1. The derivative of x is 1, the derivative of 1 is 0. That's there. Okay, if g of x is 2x and I take the derivative, I get 2. Now, some people will say, okay, well, I'm just going to take the derivative first and the second and multiply them. So let's see where that gets us, though, and I'm going to spell that out in a minute. All right, so right here, this is where I wrote this. Okay, so sometimes people will think if they have two functions multiplied, that looks like this on the right, then they just take the derivative of the first, multiply by the second. So if I take the derivative of these two and just do f prime of x times g prime of x, I get 1 times 2. However, we can see that if we take the functions f of x and g of x and multiply them, we would end up getting 2x squared plus 2x. So now, I think we'd all agree that this denotes I took f of g and multiplied. So that's this stuff right here. Okay, if I take the derivative of that, I get 4x plus 2. So I can see that just multiplying the derivative of the first times the derivative of the second does not get me where I want to go. So the key thing to keep in mind here is when you take the derivative of two functions multiplied, we cannot, however you want to write that, we can't just take the derivative of the first and multiply it by the derivative of the second. All right, however, if you're thinking about actually doing this, you probably don't want to take the original functions and just multiply them together for two reasons, really. I guess it's simple enough to do in this, but if you get more complex functions, then they might not distribute this nicely, which means that it's not really an option to differentiate, how this is on the right. Therefore, we need some type of a rule, some type of a process that we can follow. So notice this. I'm going to write this out, and let's see what we get. Let's say I want to take f prime of x times g of x, okay, plus f of x times g prime of x. And I'm sorry, I'm going to take a quick time out here. So my boyfriend is currently on Zoom with his family, and it sounds like they're playing like code words or some game. So I really hope that you can't hear, but I'm sorry if you can, and I'll try to make them be quiet right now. It just means they could have been talking through this. Okay, so now that I've written this out, I'm going to substitute everything in that I have for my table. All right, so in my table, I see that f prime of x is 1, so I'm going to write that in. I see that g of x is given as 2x, so I'll write that in. Okay, I'm going to write the plus sign that I have here. F of x from my table is x plus 1. And g prime of x from my table is 2. All right, so here we have 2x plus, I'm going to distribute my 2, so 2x plus 2. And I see that I end with a 4x plus 2. All right, so I know that I can't just take the first, multiply by the second. I'm not always going to be able to multiply the originals together and then come up with something that's going to work out. So this gives me perhaps, possibly, a process that I could follow. All right, let's try this again and see if we get the same result. All right, so new table. Notice that if I take the two derivatives, f prime of x and g prime of x, and multiply them, I get 2x. However, if I figure out what the product of the functions actually is, which is x cubed, when I take that derivative, which I do want the derivative of the product, then I just get a 3x squared. That's not the same thing, so we can see again, okay, this isn't right, there's something different. Let's try the same equation we had above. So f prime of x times g of x plus f of x times g prime of x. All right, so if we go through that and substitute with our table, f prime of x is 2x, g of x is x, plus f of x is x squared, and g prime of x is 1. All right, working through that, we get a 2x squared here, plus, that should be a 1, sorry, plus x squared, which is in fact 3x squared. Okay, so here we see, all right, like that's worked twice. The thing is, we want to make sure that it works all the time. All right, so at this point, you're probably thinking, well, she pretty much just gave it to me, which I did, but we want to keep in mind that technically in math terms, if you just show something is true once or twice, you haven't proved that it's true for everything, that it works for everything. The equivalent to this is if you maybe ask one person a question, they answer, and then you're like, all right, that's true for everybody. So let's say I go around the math department and I give a survey to some of my colleagues, and I ask a couple people like, hey, do you think math is great, or do you love math? And they're both say yes. And I'm like, all right, cool, now everybody does. Right, that's the equivalent of saying something is mathematically true in one or two examples, which means that it has to be true for everything. So how do we make sure that something's true for everything in math? We have what we call formal proof. So I'm going to show you what the product rule is and what the proof for it looks like. I'll go through it briefly, and I typed it all out just to save a little bit of time, but I do want you to understand and recognize that all of this stuff can be proven, and it all stems from the limit definition of a derivative. So all of it's coming from there. If you're ever struggling during this and you think, oh my gosh, this is so hard, just think, hey, at least I don't have to use the limit definition of a derivative on everything, because you're going to see that it's real tedious. Okay, so let's get back to the product rule. All right, I actually wrote the product rule out a couple times above, but I'm going to spell it out now. So the product rule tells us that for differentiable functions f and g, okay, if I have f of x times g of x, aka the product of two functions multiplied, that is, and I want the derivative, that's equivalent to f prime of x times g of x plus f of x times g prime of x. If you wanted to write this in Leibniz notation, okay, you take the derivative, so d dx of f of x times g of x. All right, and that would just be the derivative, so d dx of f of x times just g of x without the derivative, okay, plus f of x times the derivative, so d dx of g of x. Okay, for now you can use either notation. You'll absolutely have to get comfortable with the Leibniz notation pretty soon though, so I think it's a good idea to get some practice in with both. Okay, the way I usually think of this is in words, so I tend to think of a lot of things in words that I can just sort of say to myself. So the way I like to think of this is, the derivative of the first, so f prime, times the second, plus the first times the derivative of the second. So when I do the notes in the first couple, I'll write out all the steps with the primes and where I'm taking the derivative. Eventually, when you see or hear me do the product rule, I'll say, all right, I have the derivative of the first times the second, and I'll just go ahead and take those derivatives. So if you're kind of a verbal learner, it helps you think of that. I recommend kind of saying it to yourself every time. Okay, so now the question is, well, why is this true, right? Like I said already, all of this stuff stems from the limit definition of a derivative. Okay, so remember, limit definition of a derivative, or you could say the analytical definition of a derivative, is a limit as h goes to 0 of f of x plus h minus f of x over h. Okay, here I'm going to call it like w of x plus h and w of x, just to so you don't get confused between where the f's and g's are in here. All right, so now if I have f of x times g of x, okay, I'm going to need to run f of x plus h times g of x plus h through minus f of x times g of x. Okay, so that's just running it through that definition of a derivative. All right. Okay, so now I know that, or at least maybe I remember from section 3.1, that I want these definitions of derivative to peel out from all of the algebra I do. Well, if I look at this first part right here, okay, I know that somehow I have to get to the point where I have f of x, oopsie, this is not showing, f of x plus h minus f of x over h, so that limit, k plus the same thing repeated in g's. So in order to do this, I need more terms in here, which is gonna come in handy, I guess you could say, by a little trick here. So in the first step, I know I need to get more terms in here, meaning I need to get an f of x that can go with the f of x plus h, and I need to get a g of x plus h that can go with the g of x in the second part. So if I, in the middle, doesn't actually matter where, but I put it in the middle because it's more visible, subtract f of x times g of x plus h and then add f of x times g of x plus h, notice that this is really just equal to 0. So essentially, I'm adding 0 in a fancy way. I don't change this expression at all because we know adding 0 to something doesn't change the value of that at all. All right, from here, what I've done is factored a g of x plus h out of this first part right here. Okay, so I factored the g of x plus h and I was left with the f of x plus h minus the f of x. That's what went right here. Okay, this plus sign stems from right here. All right, and then from over here, I factored an f of x plus h out. So over here, I have this f of x plus h factoring out here, and what was left was the g of x plus h minus the g of x. That is what's inside of this part right here. Okay, so at this point, things are starting to peel out a little bit. I can sort of see the definitions of each derivative building in here, but I need to make it more clear. So the first thing I did was just wrote times g plus g of h plus x over here. If you think about it, I could put this over 1, multiply it back through, and it equals the exact same thing. So I essentially just wrote that differently. All right, same thing over here. I just put the f of x plus h here. I could put it over 1 and then it'd just be the same multiplication. So that again changes nothing. Okay, from here, if I take I know I can take the limit across multiplication by the limit laws. So if I take the limit as h goes to 0 of g of x plus h, I'm left with a g of x, which is unimpacted by that h. So I can put that just multiplied on the outside. And similarly, f of x is not impacted by the limit as h goes to 0. So I can take that out. Now you can see here, you have the definition of a derivative for f prime of x, and you have the definition of a derivative for g prime of x. Therefore, this product rule is completely spelled out. All right, so I know not everybody loves the reasoning, but I think it's cool. I'm biased in saying that. But I also think it's important that you understand what's going on and that this really is stemming from that initial definition of derivative that we worked with. Okay, so now let's roll through this. Let's see some examples. Let's see how the calculations work out. As I said before, I kind of build up in the notes. So we'll start kind of simple, get maybe to medium level in the notes. Then the homework, we'll build on that even more and you'll need to ask questions. So there'll be some algebra things in there that are maybe a little bit different, some concepts that are different. Leave yourself time to ask questions about those things. Okay, so First example, let's suppose that h of x is equal to x squared times e to the x. Calculate h prime of x. All right, so since this is in prime notation, I'm going to use prime notation throughout. All right, so I noticed that when I read this to you, I said x squared times e to the x. When I say that, it means that I'm probably going to be using the product rule. So I have x squared, that's my first function, I'll call it f, times, so product rule, my second function, which is g. All right, so let's write this all out. Okay, so I have h prime of x is equal to the derivative of the first, so that would be x squared prime, because my first function is x squared, times the second, so times e to the x, plus the first function, so e to the x, or sorry, the first function, so x squared, times the derivative of the second, so e to the x prime. All right, so I have the derivative of the first times the second plus the first times the derivative of the second. I wrote down all the little primes in here. Really, eventually you'll be able to just go straight to the derivative part. Okay, so the derivative of x squared by the power rule, so I notice I have a variable to a constant, so the power rule applies, is 2x. Okay, just rewrite e to the x for the second function, plus my first function is x squared. Okay, e to the x is an exponential function, but we should remember the derivative of e to the x is always itself, so that's just going to be e to the x. All right, here, for me, I'm done. In the text, I think, I'll say you could write, so if you do WebAssign, I think they have you write something like h prime of x is equal to e to the x times 2x plus x squared, so they have you factor that out. That's not really necessary. You could just leave the little underlined answer I have here. Okay, let's move on to a second one. So suppose we have u of t is equal to 5 to the t over t squared. Okay, looking at this, when I read this to you, I could have said u of t is equal to 5 to the t divided by t squared. As this is written right now, the product rule does not apply, and that's because I have functions that are divided rather than functions that are multiplied. So if you wanted to use the product rule on this, what you would have to do is rewrite as a product. So rewrite as a product, so you can use the product rule. Okay, how do I do that? I have to remember properties of exponents. So if I have this t squared in the denominator, that means really what this is equal to is u of t equals 5 to the t, that's the numerator, times t to the negative 2. So that was just by properties of exponents. Okay, now at this point, if I read 5 to the t times t to the negative 2, it is in fact a product, which means I can apply the product rule. Doing so, I have u prime of t equals, all right, and here my first function is 5 to the t. My second function is t to the negative 2. So if I write all the steps out, I'm going to end up taking the derivative of the first, so 5 to the t prime times the second, so times t to the negative 2, plus the first, so 5 to the t, times the derivative of the second, so t to the negative 2 prime, right? Now we need to actually go through and take those derivatives. So 5 to the t is an exponential function since I have a constant to a variable. This means we use the exponential property. Therefore, my derivative is 5 to the t times the natural log of 5. I'll rewrite the t to the negative 2 plus 5 to the t. Okay, with the t to the negative 2 prime, meaning that derivative, since I have a variable raised to a constant, I can apply the power rule. So I have times a negative 2 t to the negative 3. All right, so technically at this point, I'm done. I've taken my derivatives. For me personally, it's okay. However, if you choose to leave your answer like this, I highly recommend, or actually you need to, Okay, you must write. So if you leave this way, you must write that times symbol. If you don't, I'll erase it real quick. All right, what does that look like if you don't put times? It looks like you're subtracting the 2t to the negative 3 rather than multiplying. So if you choose to leave it like this, you need to be really careful with your notation and make it very clear that you're multiplying, you're not subtracting. To be safe, I recommend writing it like this. So 5 to the t times ln 5t to the negative 2 minus 2t to the negative 3 times 5 to the t. Okay, here it makes it more clear that you're not just subtracting, and really, if you don't write the multiplication, it's pretty safe, and that's because t to the negative third, negative 3, and 5 to the t are different terms. They're not like terms, so there isn't really confusion that you're combining those together. All right, last thing on this, if you do WebAssign, I believe that the book makes you drop the t to the negative 3 back into the denominator, so you'd have 2 times 5 to the t over t to the third. It makes you do the same thing over here, and it might even make you find a common denominator and put all those together and then simplify. I'm not sure at the WebAssign standards completely, but I do want to forewarn you that this is going to take a lot longer to do if you choose to do the WebAssign, just because of the amount of simplification that you have to do. In terms of answer in the back of the book, it definitely will not match this middle step. Sorry, I guess this is where I left it, even if you did it right. So what you have to do is either plug a number into both your answer in the back of the book and make sure they're the same, or if you're really worried about it, you could always post on the discussion board and compare with people, and then I'll check as long as it's, not maybe a Saturday or Sunday, which it won't be because this is all due Friday. All right, let's try another one. So this time, let's suppose we have f of x equals pi to the x times x to the pi. We're going to calculate df dx. All right, so when I read this, I said pi to the x times x to the pi, which implies we will use the product rule, with our first function being pi to the x, and our second function being x to the pi. Okay, so going through this. Okay, I'm going to do this in the Leibniz notation since it originates in Leibniz notation. So I have d dx of pi to the x times x to the pi. Okay, that's equal to the derivative of the first. So if I use Leibniz notation, I denote that by writing d dx of pi to the x times the second, so times x to the pi, plus the first is pi to the x, times the derivative of the second is d dx of x to the pi. All right, so now we need to go through and actually take our derivatives. Right? If we take the derivative of pi to the x, we need to remember that pi is really just a constant number. So we have a constant raised to a variable, which means we will apply the exponential property. Therefore, we have pi to the x times the ln of pi times x to the pi, so I'm just rewriting that part here, plus pi to the x, just rewriting the plus and the pi to the x. Now I need the derivative with respect to x of x to the pi. So on this, I have a variable raised to a constant, which means the power rule applies. So what I have is times pi x to the pi minus 1, right? For me, you'd be done here. If you were in the text, you'd have to simplify a lot more. All right, so that gives you the concept behind the product rule, some examples. When you go through your homework, you will see things that are more complex, but you do have the tool in your tool bag for it. So you have the product rule. Once you notice you have those things multiplied, it means you can use it. It might be a little more complex. You might see easier examples, but you do have the tools. So please give that a try and then ask questions. In the next video, I'll go over the quotient rule.